Hi class, I thought we'd do an example of binary integer linear programming. The theme of the problem is Lumberjack competitions. So you can find out more about these different events that I'm going to talk about at the Wikipedia page or elsewhere. But what we have here is a competition with 1, 2, 3, 4, 5, 6 events. Certain events are competed in by males and certain events are completed in by females in the way that competitions currently work. And we have several members of our Lumberjack team. We've got Will, Bill, Anil, Groot, Emerald, Jill, and Avril. And here are their average times for each of these events when they do them individually. So Will takes 12.33 seconds to complete a 60-foot speed climb. Avril takes, on average, 14.4 seconds to complete the boom run. And our job as team captain is that we're trying to assign one competitor per event. So we need to decide which of our teammates is going to do the 60-foot speed climb, which is going to do the boom run. And each competitor is only allowed to compete in one of these events. They can't do multiple ones. So even though Will actually has, I think, the best times in all of these events, we can't use Will more than once. He's only allowed to compete in one of these events. We want to minimize the total time to complete all the events. And this can be solved as a binary integer linear programming problem. The first thing that I'd ask you to do is pause the video and think, what are the decision variables of this problem? Remember, I'll tell you up front, every one of the decision variables is either 0 or 1. What is that 0 or 1 going to represent? What are our decision variables for the problem? I'll give you a hint. We're trying to decide for each event who is going to compete in that event. Okay, another way of thinking about it is our decisions that we have to make is will compete in the 60-foot speed climb? Will compete in the boom run? Will Groot compete in the boom run? And so you see where this is going. Well, what we're leading to is that the decision variables, the 0s or 1, will be the answers to these questions. Is Bill going to compete in the 60-foot speed climb? Is Anil going to compete in the 60-foot speed climb? Is Groot going to compete in the 60-foot speed climb? If it's 0, then that means no. If it's 1, that means yes. And it turns out that every one of these other constraints can be expressed in terms of these decision variables too. And so what I'm going to do, I think it's actually easiest, rather than writing this one down, we'd have a lot of handwritten equations. These things are actually easier to solve straight in Excel. So what I'm going to do, what I'm going to have is a separate decision variable for every element on the table here. So I'm just going to copy this table, and that's how I'm going to start by solving this problem. All of these cells are going to now be decision variables. I'll start them all out at 0. And all of these cells, I'm going to start out at 0. This means that currently we have nobody assigned to compete in any event. And what we're trying to find is one competitor per event, each competitor to compete in at most one event. So for example, if I was putting together my team and I want to say that Bill is going to end up competing in the 60-foot speed climb, then I would end up having a 1 in here. Now I'm not going to enter that myself. Excel is going to do that for me. I should probably change these to be integers. Okay, 0 or 1. So Excel is going to choose this for me, but ultimately I'm going to want to put 1s in the places where the teammate is going to be the one to compete in that event. Okay, so for another example, this here means that Avril is going to compete in the boom run. Okay, now how do we do our constraints? That's our decision variables. Okay, so those are what our decision variables mean. How are we going to figure out our objective function? Suppose that Excel had chosen some sort of solution that looks like this, maybe. Okay, so this means that I've got an example. One person is competing in every event. Bill is competing in the 60-foot speed climb. Will is competing in the boom run. We've got Groot is on the hot saw. Emerald is on the standing block chop. Avril's on the boom run. And Jill is on the single buck saw. So one person is in each event. And also, each person is used only once. So Will only competes in one event, Bill only competes in one. Anil actually doesn't get to compete at all, just too slow, unfortunately. Groot gets to compete here, etc. So each person is used exactly once. So this is an example of a solution that satisfies the constraint. It might not minimize the total time to complete all the events, but how would we measure what is the sum of the times that it's going to take for all of these events? So we've got the decision variables here. How are we going to compute the objective function, the total time it takes to complete all the events? So maybe you can answer just a partial question. How much time is it going to take to complete the 60-foot speed climb, considering that Bill is the one who's doing it? Okay, now how much time is it going to take to do the boom run, considering that Will's the one who's doing it? Okay, if you know the time that it takes to compete in each of the events, then what's the total time for all the events? Okay, so one way that you might be able to do this is you could say that we're going to use this sum product of the times that it takes and our decision variables here, the corresponding ones. The time that it takes to do the 60-foot speed climb is Bill times 12.41. Turns out there's more digits here, so we can just extend this down, right? And this is the times that it's going to take for each of these events. And then the total time. Sum of all of these is the total time for the competition. We're trying to make this number as fast as possible. So our objective is to minimize that time there, right there. Another way that we can express that, by the way, we just want to take the sum product of actually everything in the table with everything in this table. And where there's no entries, it's going to be 0 times 0 and just adding those. So you're going to see we're going to get the same thing there. So very easy to compute the objective function if you use decision variable 0, 1, representing whether each person competes in a given event. Now you might say, well, wait a second here. What if you had, one there, two, and also one there and one there? Well, if these were correct, then this still is the time that it would take to complete the whole competition. This is just happens to not be a feasible solution, right? We have Will competing more than once. We've got both Will and Bill competing in the 60-foot speed climb. It's the job of it's not the job of the objective function to prevent that from happening. It's the constraints that are going to prevent that from happening. Okay, so forget about that possibility for a second, and what we really need to do is think about what constraints we need to add to prevent that sort of thing from happening. So the constraints that we have is that one competitor per event. Okay, so how are we going to handle that constraint? What's the relationship between the decision variables and that constraint? Okay, so you can see that if we've got decision variables 0 or 1 for given each person competing in the event, then we know that the sum of the decision variables has to equal 1, exactly 1 competitor per event. So I'm just going to have the sum of all these decision variables. And look, you can see that they're all going to be 1. We've got one person competing in each event. One person per event. And I'll probably write exactly. All right, each competitor can compete in at most one event. Okay, so how do you decide how many events a competitor is competing in? How are you going to make sure that they don't compete in more than one? Same sort of idea. Let's just sum the columns in this case. The sum of all these is the number of events that Will is competing in. The sum of all these is what each person is competing in. So Anil is not competing in any. If Bill had another entry down there, then he would be competing in 2, and that's not going to be allowed, right? This is not going to be a valid solution because these numbers down here, the sum, of the number of events each person competes in, can be at most 1. 2 is not going to cut it. And we want to minimize the total time to complete all the events. I don't think we have any more constraints here. I think that if we just make sure that exactly one person, each of these numbers is exactly one, that means exactly one person per event. If each of these numbers is no more than one, then that means that each competitor can compete in at most one event, and we want to minimize the objective function. So let's go ahead and set this up. We're going to go to Data and Solver. So our objective cell is going to be K21. That is the time, the total time. We're going to try to minimize that, and we're going to try to do that by changing the variable cells. Well, all of these are variable cells, and also all of these are variable cells. We don't want to select these cells that actually aren't zeros or ones. We'd have to make sure that those are all zero, so we might as well just not make them variables. We're going to add constraints. All of these ones, these are the number of people competing in each event, exactly one person per event. We're going to constrain that to be one. We'll say add. And then the second one, each competitor can compete in at most one event. All of these, the number of events each person competes in, has to be less than or equal to 1. And finally, we're going to add in the constraint that all of our decision variables, these ones here, have to be integers. In fact, they have to be binary. We're going to select binary bin. So we'll add that, and these ones as well. These are also decision variables. They need to be binary too. So we'll say OK. All right, so I think that we have our objective function, and we have our different kinds of constraints. All these constraints are considered. The last thing we need to do is choose our solver settings. It says make unconstrained variables non-negative. Well, first of all, Excel is treating these as binary. That means they're either 0 or 1. We can leave this checked or unchecked. Binary numbers can only be 0 or 1, so they're always going to be non-negative. So that doesn't really matter much. Simplex LP is what we want, and we're going to go to the options. And it's important, if you want the exact answer, that you set the integer optimality to 0%. So we're going to set that. Okay. I think that we can solve it now. All right, let's keep the solver solution and take a look at this, see whether it satisfies our constraints or not. It looks like it does. There is only one person in each event, and each person competes in at most one event, and it found a lower value of the objective function than we found before. So if we're confident we've set up the problem correctly, then this is our answer.